All right, thanks everyone for coming. My name's Tim Pettersen, and I'm a developer from Atlassian. Actually, you may have seen me speaking at lunch a few minutes ago. And today I've got a pretty cool story to tell you about an interesting collaboration between Atlassian Bitbucket and GitHub, who are traditionally fairly staunch competitors, but we've decided to team up on a particular project that extends Git, everyone's favorite distributed version control system. Are there any Mercurial users in the audience? That's totally okay. I use Mercurial too. No? Okay, cool. So like many great stories, our story today begins in Paris. It was April 8th last year, 2015, the day before the annual Git Merge Summit, which is a big conference that happens once a year in various parts of the world to talk about everything that's going on in Git. Now, the day before that, they have a contributors summit where all of the regular contributors to Git get together and talk about how they're going to develop Git over the next 12 months. And there was a really interesting conversation that happened at that summit between an Atlassian named Nicola Pellucci and a GitHubber named Rick Olson. And it went something like this. Nick from Atlassian said, hey, Rick, we've been working on this interesting extension to Git that solves the problem that we have with storing and tracking large binary files. So we've built this new extension in Go because we want it to be cross-platform and portable. And we're planning on announcing it at our track session during the Git Merge conference tomorrow. And Rick said, Nick, that's kind of interesting because at GitHub, we've also been working on a solution to the problem that Git has with tracking large binaries. We've also built an extension to Git in Go because, again, we wanted it to be portable. And we're also announcing it at our track session at Git Merge directly after yours. At this point, Nick went, what? That's a picture of James Watt, by the way. And Rick went, totes. It seems we've built two different solutions for the same problem. What do you call yours? And here's where it gets really weird. Nick said, well, we call ours Git Lob, after long objects like you might find in a database. And Rick said, that's funny, because we also picked a three-letter acronym beginning with L, Git LFS, for large file storage. And after a bit of back and forth between Nick and Rick, and then eventually Atlassian and GitHub, Atlassian decided to open source and archive the Git Lob project and start porting some of its features over to Git LFS. And that's how you have two traditional competitors cooperating together on the same product. Now, this is pretty exciting for the Git community because that means there will no longer be sort of fragmentation. Git is inherently a portable data format, so it's very easy to move between different providers. And the fact that we have the same solution to track binary files means that we keep to that. And it was also really easy for us to do this because they were designed in such a similar way. They're both using exactly the same extension points in Git, and they were both implemented in the same language. So it was relatively straightforward for us to port over some features from Lob to LFS. And that's why I'm here today to talk to you about the Git LFS project. Now, I've done quite a lot of Git evangelism in the past, and the reason I'm really excited about Git LFS is not just because it's a really cool piece of technology, but because it also opens Git up to all of those different development teams who, for one reason or another, have been stuck on centralized version control. Because if you were building a game, for example, a modern AAA plus title, these days you're talking about gigabytes of assets. There's textures, there's audio, there's full motion video, there's huge models, and all of this stuff, it would be really convenient if you could track it alongside your source code. However, unfortunately, Git has a bit of a problem that we'll get to in a minute with tracking large binaries. Similarly, if you're a researcher and you want to store your large data sets or training data for your neural networks alongside the code and scripts that you're using to build these, it would be really convenient if you could do that in the same Git repository, but that's actually really tough to do with just raw native Git. And even traditional web software developers like myself, there's a whole bunch of use cases where you might want to store large binary data. For example, at Atlassian, we write huge regression test suites for all of the software that we build. And as part of that, it would be nice if we could version database snapshots alongside our source code. Whereas at the moment, we have to use an external dependency management tool and then pull those down and version it separately, where it would be much more convenient if we could have it alongside our source code. So Git LFS means that all of those developers who are stuck on CVS or Subversion or Perforce or other centralized solutions can now start switching over to distributed version control, which is really exciting. So there's kind of four broad topics that I want to cover today. The first is I want to identify why Git has such a hard time tracking binary content in the first place. And as part of that, we'll take a look at some of the computer science behind how Git stores data on disk. Then I'll talk a little bit about how Git LFS extends Git and how it solves the problem with storing binaries. Then I'll give you some tips for converting your existing repositories over to Git LFS if you're already storing large binary content. So for example, if you're a Java developer and you have jars checked in, hopefully you're using something like Maven or Ivy to version your dependencies, but if you're not, then potentially Git LFS could be a solution for you. And then finally, I'll give you some tips for using Git LFS and Git in a team context. So first of all, to understand why Git has such a hard time versioning binaries, you need to know a little bit about the Git data model. Now, when you think about version control, you're probably thinking about different revisions or snapshots of your code over time. Now, in Git and a few other version control systems, these are known as commits. And these commits are related to each other. They're not just sort of floating in space. Specifically, each commit has a reference to its immediate parent or parents in the case of a merge commit. Now, this data structure is known as a directed acyclic graph, or DAG. Now, the reason it's directed is because each commit, when it's created, has those references to its parent or parents. So you can see it's got a direction between the nodes and vertices. And it's acyclic because each of those commits, as they get created, are unchanged from that point on. Every time you create a new commit, you're adding to that, but you can never create a cycle in that graph. Now, if we add in a couple of branches, which are more generally known as references, so a tag inside your Git repository is almost identical to a branch. It's just treated slightly differently. So now if we add those in, we've got something that looks pretty much like a complete model of what your version control history looks like in a Git repository. Now, to understand why Git has such a hard time with binary content, we need to look a little bit deeper at these commit objects and how they actually store data. So there's a command called git cat file. If you use that with the -p for pretty flag and pass it a SHA-1 address, which is just a commit identifier, it'll show you the actual contents of one of these commit objects. And they're actually pretty lightweight. As you can see, they've got a reference to the parent, which is the commit that immediately preceded it, as we were discussing before. And then they also have a reference to this tree object. Now, that tree represents the top-level directory of your repository. So it's kind of like a directory on disk. We'll see what those tree objects look like in just a second. And then you've got some additional commit metadata, which is pretty lightweight. Who created the commit, when it was created, who authored the code, which is typically the same person who created the commit, depending on what sort of Git workflow you're using. And then finally, you've got a commit message as well, which is what you type in when you create the commit at the command line. Now, these identifiers, or commit IDs, as I mentioned, are SHA-1 hashes. And they're actually a SHA-1 hash of the contents of this commit object. So it's literally just passing this text through the SHA-1 hashing algorithm and taking what comes out and then calling that a commit ID. Now, every Git object inside the Git data model has one of these SHA-1 hashes of their contents. And this has some really interesting properties that we'll see in just a second. So if we take that tree object, which as I mentioned is kind of like the top-level directory of your Git repo, and pass it to that cat file command, you can see the contents of it. And it looks, again, just like a listing of a directory on disk. You've got some file modes, you've got the type of the object, which is either a blob, if it's an actual file, or a tree, if it's a nested directory. So these trees, called app and config, are the top-level directories sitting inside my Git repository for a Node.js app in this example. Now, if we keep recursing down through the data model and calling cat file on each of these trees and blobs, you eventually map out the full contents of my file tree at that particular commit. And this is where we start to see the problem with large binaries. And if we whack in another branch name here, you start to see kind of a complete reference of the Git data model. But Git creates a new one of these tree objects every time it creates a commit. And by default, it ends up creating a new blob or tree every time you modify one of those files on disks and create a new commit. Now, because it's content addressable, so the SHA-1 hashes of each object are actually the file name that Git uses to store that file on disk. So that makes it really easy for Git to reuse these objects when they don't change. But every time you change a file, you're creating a new one of these blobs. And every single tree back up to the root will have to be rewritten because they have a reference eventually to one of those blobs. Now, each of these blobs is zlib compressed, and they are eventually delta encoded. But with binary files, because the typical binary file format already has some sort of compression applied to it, it means that they don't really compress very well. So in the trivial case, say where we have a repository which is just one level deep and only contains a single file, say a reasonably high-resolution photo of an elephant, if we go and change, say, the hue of that elephant to pink and then create a new commit, then that's going to double the size of our repository. And every time we make a modification to that, it's going to bloat our repository more and more and more and more. Now, this isn't just a problem that Git has. Any version control system has to solve this problem in some way. It has to know how to store efficient deltas of each of these files. And for some file types, there is no way to really store an efficient delta without knowing some more semantic about what that file actually contains. But the reason Git has such a hard problem compared to, say, Subversion or Perforce is because Git is a distributed version control system. So after I've made these modifications to that file, I have to push those up to the server, which is kind of the same as if you're working with a centralized version control system. However, what's different is the rest of my team, because when they do a clone or a fetch, they're working with an entire copy of the repository's history, they have to pull down every single version of that file. Whereas with something like Subversion, you're typically only pulling down the latest commit. So the rest of the kind of intermediate history, you don't have to copy from the server. So as the Git repository grows, our fetches and our pushes slow down more and more and more, and then the load on our Git hosting solution grows and grows and grows, and eventually everything comes to a grinding halt, which is why people hack together solutions around Git where they don't have to store binaries directly inside it. So this is where Git LFS solves the problem. Now, as I mentioned, it's a joint project between Atlassian and GitHub, and there's actually been a few other attempts to solve this before. But Git LFS, I think, absolutely is the nicest attempt to solve this so far, in that it works almost 100% transparently with your existing Git workflow. So unlike Git itself, the learning curve for switching to Git LFS is relatively straightforward. And again, migration is also relatively simple as well, which we'll look at in just a second. So the high-level, kind of in a nutshell picture of how Git LFS works is instead of storing these large blobs or binary files directly in your repository, instead, you store a pointer file inside your repo, which is a few bytes, and that contains a reference to where that large file sits in separate storage. And when a developer does a git push, for example, after they've made some modifications, those large files get transferred to a separate LFS store. Then the rest of your Git DAG gets transferred to your Git host as normal. So every time you make a modification, instead of adding multiple megabytes or gigabytes to your repo, you're only adding this handful of bytes when those pointer files change. Now, the actual saving comes from when developers start retrieving content from that repository. So if I run a git pull on this repo, the DAG gets transferred from my Git host as normal, and then I only retrieve the versions of that large file that I actually want to work with, which by default is just the tip of the branch that I've been checking out. Now, if we whip out our git cat file command again and take a look at one of these pointers, you can see that they are ridiculously small. There's a version URI, which is just a fancy modern way of doing a version number. There's an object ID, which is a SHA-256 hash of the object's contents. And then there's a size, which is the size in size in bytes on disk of that large object. Now, you'll see we're using a SHA-256 hash here instead of a SHA-1 hash, as you find in vanilla Git. There's a couple of reasons for that. The first is that Git is now 11 years old, and SHA-1 was kind of thought to be pretty much perfect at the time. However, there have been shown to be some theoretical weaknesses in the SHA-1 algorithm. So SHA-256 is just a more modern standard, which is slightly more secure. And also, depending on your choice of LFS storage, there are some modern ones like AWS S3 that has built-in support for SHA-256 validation or hashing of objects that are stored inside it. So you can leverage that by using the SHA-256 hash instead. So installing Git LFS is ridiculously simple. As I mentioned, it's built in Go. So there are versions of it available for basically every platform that Git is available on. You can install it with Yum. You just need to make sure you have the extra packages for Enterprise Linux repository installed first. Or if you're on OS X, you can use Homebrew. Or you can just go to the Git LFS site and download a binary for your particular system. And once you've got it installed, all you need to do is run that Git LFS install command, and it'll initialize it for you. Basically, all that command does is add a new entry to your global Git configuration, which sits under .gitconfig in your home directory. And what the configuration does is it sets up a thing called a clean filter and a smudge filter and binds that to an overall LFS filter. Now, these are a couple of different mechanisms for intercepting various Git commands. Specifically, the clean command allows you to intercept files that are being staged by the git add command. So instead of just being written straight into your repo as an object, it gets handed off to the Git LFS clean command instead. And the smudge command is kind of the reverse of that. It gets invoked every time you check out a file into your work tree from your repository. So these two things are going to be what transforms our large objects into pointers and then back into large objects for use. So once we've run git LFS install, we can run git LFS track and pass it a file pattern to start tracking large content inside your repo. Now what this does is it adds a new entry to the git attributes file inside your repo. So this is actually a native Git concept that allows you to bind certain behaviors to certain file paths. What it's doing here is binding everything, or all files matching star.mp4 to the LFS filter. And filter equals LFS, diff equals LFS, and merge equals LFS is just saying, hey, filter files through the LFS filter whenever they're being checked out or added. And also, you should use LFS whenever you're diffing or merging. And that final minus text is basically saying, don't try to create text diffs for this file type, because that's not going to work very well for binary files. So to see how these clean filters work in action, let's take an example where a developer is adding a single file into their Git repository. And you might imagine they've got a massive video of the MP4 variety. When they run git add, usually Git would just copy that, or take a hash of, usually Git would just copy that file directly into the Git objects directory after zlib compressing it. Now with Git LFS, because we've got that filter defined, instead it hands it off to the Git LFS clean command. Now what that does is it takes a SHA-256 hash of the object's contents, and then it writes out the object's contents into the .git/lfs/objects directory, which sits inside, I guess alongside your repository metadata, but it's not something that Git itself actually knows about. And you can kind of think of that directory as a temporary cache of large objects that you've committed to your repository, but you haven't yet pushed to the server. Then, once it's done that, it writes out that SHA-256 hash alongside that version URI and the size to one of those pointer files on disk. And then that's what gets added to your Git objects directory. So this is where the space savings come in. Instead of that multi-megabyte MP4 file, it's just adding a few bytes into your Git objects directory with the rest of your DAG. Now, when you run the git checkout command, the opposite thing happens. It takes that pointer file from your git DAG, passes it through the git LFS smudge command, which goes off and looks in that local objects cache to try and find a matching blob that contains your big file data. Now, at this point, if it can't find it in that local objects cache, it actually reads through to the backing LFS store associated with your Git repository. Once it's tracked that down, it writes it out into your work tree, and you can start working with it as usual. Now, I must admit, I've been kind of wasting your time for the last 5-10 minutes talking about clean and smudge filters, because as a developer, you don't actually need to know about these pointer files or how these things work, because literally you're just running git add and git checkout as normal, and it does all the translation from large file to pointer and back again without your knowledge. So you can literally just use the same workflow as you're already using. Now, I want to talk a little bit about how you transfer these large objects to and from the server. Because so far, I've really been talking about how you interact with a local repo. And of course, eventually, you're going to want to publish these changes for the rest of your team. Now, the way that it intercepts a push command is via a thing called a Git hook. Has anyone worked with hooks before? Anyone? Yeah? Oh, OK, cool. Most of the room. Nice one. So if you haven't worked with hooks before, take a look in the .git/hooks directory of any repository you have on disk. Git actually pre-generates a set of sample scripts for you. There's, I think, over a dozen anyway that do all sorts of interesting things with Git lifecycle commands. For example, I use the commit message hook to precede commit messages with the issue key taken from my branch name. At Atlassian, we have this convention of making sure that we annotate every commit message with the issue that we're working on from Jira. So that just saves some time from going and doing a manual lookup. But you can also do things like use a post-update hook on the server to notify HipChat or Slack when someone commits to your repository, or even create pre-commit hooks, which run before a commit is created on disk. So some of our front-end developers go off and run some JS hint and other linters to make sure that they haven't committed any style violations when they're first checking in their front-end code. Now, the one that Git LFS uses is a thing called a pre-push hook that probably somewhat intuitively intercepts the push command and runs immediately before it. So when you transfer when you do a push and you've got some new large objects that you've created locally, you'll see some output from Git LFS saying that it's transferring it to the server. Now, one thing that you won't see here is any prompt for authentication. Now, that's because Git LFS piggybacks off your existing authentication with your Git host in a really neat way that I'll show you in just a second. Similarly, with git pull, you'll see some output from that smudge filter when it has to read through to the backing store and says that it's downloading some files. And one of the really cool things about Git LFS, and which I think it's alone in terms of the solutions for binary file management in Git, is that it also works transparently with SSH as well. Although there is a little bit of work you have to do on the side of the Git server implementer to make that happen. But that's OK. That's Atlassian or GitHub's job to solve that. So I want to take a moment and talk a little bit about how this auth protocol works, because it's a pretty cool use of some interesting technologies. Now, I mentioned that it works over both SSH and for both SSH and HTTP repositories. And this is really interesting because the LFS API that you use to store these objects is actually HTTP only. But it can bridge from the SSH protocol, which I'll show you in a sec. But it's also flexible enough to not only work in the case where you've got a Git server with an embedded LFS store. So Bitbucket Server, one of the products that I work on, adopts this model where the LFS store just sort of sits alongside your existing Git repos. But it can also work in the case where you have a Git server and then your LFS store is completely segregated from it. So if you work in a very actually that's probably a bad example, but for example, you could have a Git server that sits on your local network and doesn't actually have access to the internet at all. And then you could have a bridged network where you have access to S3. And you can use S3 as a store, even though your Git repo is sitting on a separate network that can't contact it. And it does this by proxying the knowledge about where these large files are sitting via the client. I'll show you how that works as well. So first of all, let's take the simple case where we're cloning from an HTTP-hosted repository. And we've got some LFS files hosted alongside it. So when a developer runs git clone and they pass an HTTP repo, the pack files get transferred over the wire as normal, so that's just standard Git. But then that smudge filter that we saw before starts being invoked every time the Git LFS process, every time the Git checkout process comes across one of these pointer files sitting in your repo. So instead of writing out that pointer file on disk, it runs via the smudge filter, as we saw before. And at this point, the smudge filter sends a request to the Git LFS API saying, hey, I found this pointer file. It's got this SHA-256 hash. Do you have the content that I need to write out on disk? Then the server responds telling the client where to grab that content from. And then it goes off and retrieves it from that LFS store. Now, I mentioned before that there was no authentication prompt when that download occurs. And that's because the server actually tells the client how to authenticate with the LFS store. So with the client, when they're contacting the HTTP API, just append a certain path onto the repo address in order to hit that. And they pass up a JSON structure saying, hey, this is the object ID that I need, and this is the operation I want to perform. So either a download for a clone or a fetch or a pull, or an upload if it's a push. Then the server responds with a similar JSON structure, except with some hypermedia actions appended to it. So it's saying, hey, you can download the object at this location. But it also says, here are the headers you need to apply to that request in order to authenticate with that storage medium. So in the case of Bitbucket Server, because it's embedded, we just have a really simple JOT token, which is signed in a manner that we know that we can use to verify that a particular user was handed that JOT token. But it's really up to the implementer as to how to implement that. So you could have a bearer token or basic auth or anything else there that you want to use with whatever storage medium you're using. So for S3, you might have some S3 credentials put into a basic authorization header, for example. So that's how it works with a pull. Now for a push, it's pretty similar, except instead of being triggered by that smudge filter, it's triggered by that pre-push hook. And the user specifies an upload instead of a download action. And then the server says, hey, yes, you can upload that file over here, and again tells the user tells the user which credentials it needs to use to authenticate that request. Now there is an additional step here as well, where the LFS-aware Git server can say, after you've uploaded that object, come back and verify with me that that's occurred. And this is what gives the LFS server implementer the flexibility where they can actually have no direct access to that LFS store. Because they can, when the client comes back and tells them that that file's been uploaded, they can record the fact that that's sitting in that store. So that means that at that point, you could have a fully segregated store, and still your LFS-aware Git server can have full knowledge of what's actually being stored there. And that looks a little bit like this, very similar to the download actions, except now you have an upload action and an optional verify action. Now, SSH is a little bit more complicated. because the way that we've been making that initial request to the LFS API saying, hey, I want to upload or download this object, is by appending the location of the API to our repository's HTTP URL. Now in SSH, we don't have an HTTP URL, and we can't really make any assumptions on where that HTTP URL exists based on the SSH command, based on the SSH location. At least not if we want it to be portable across providers. So instead, there's an extra step that has to occur here, where the client asks the server over SSH where the HTTP location of the LFS API is. And the way this works is that there's a special LFS authenticate command that the server has to implement and grant permissions for whatever the Git user is to invoke it. And then it takes two parameters, the repository, an identifier for that repo, and then also the action, so either a download or an upload again. And then the server responds with another little piece of hypermedia, and all that hypermedia is telling you is the location of that HTTP API, and again, the headers that you need to apply in order to authenticate it. So that's all pretty cool, and I think it's a pretty interesting piece of client-server auth infrastructure. But what I've told you so far is a little bit confusing in that the end of the LFS API is called batch. But Git smudge filters are invoked once per file that gets checked out on disk. So in practice, if you're just using git add and git checkout to work with your repository, you're only ever going to be making a single request for a particular object using this batch API at a time, which is pretty inefficient. Because that means, if I check out a repository with like 100 LFS files in it, it's going to have to do that back and forth dance with the LFS API 100 times, and then make 100 requests to the storage medium, wherever that is. Now, as of version 1.2 of Git LFS, there's a new Git LFS clone command that actually disables the smudge filter and then batches up a huge request with all of those pointer files, SHA-256s in it, and then grabs all of the download URLs and then goes off and downloads those all in parallel. So if you're doing an initial clone, or if you're configuring a CI job or a CD job that uses Git LFS, I highly recommend using Git LFS clone if you're doing a clean fetch, because that'll be much, much more efficient. Particularly if you're running on Windows. At the end of the day, Git is kind of a collection of shell scripts in native C, and it doesn't really have a persistent process. You might notice when you run a Git command in your terminal, it's sort of jumping back and forth between all of these different commands. On Linux or on OS X, that's OK, but on Windows, the overhead for forking a process is much higher. So you'll notice, particularly with Git LFS, if you have lots of files being tracked, a clone on Windows can be super, super slow. Just for reference, are there any developers working on Windows here? Nope? OK, cool. All right. I'll steer clear of the Windows-specific stuff for the rest of the talk. So that's how Git LFS works internally. Now I want to talk a little bit about how you can convert your existing repos over to use the Git LFS standard. Now, I may have misled you a little bit before when I mentioned that the Git LFS track command will let you start tracking LFS content. It does, but it only really works if you run that command when you first introduce a large binary into your repository. If you go and run Git LFS track on an existing repository that already contains large objects throughout its history, then it's not really going to do much for you. In fact, all it's going to do is add a few bytes to your repository size, because you still have all of these blobs sitting around in your DAG. Now, for those of you who've been using Git for a while and think, OK, I need to go rewrite some history, you might reach for the git filter branch command. Has anyone used filter branch before? Cool. Can anyone tell me what this command does? So git filter branch is kind of the Swiss Army knife of like history rewriting. So it's powerful, but it's incredibly flexible. It's kind of mean to try and ask someone to parse a set of filter branch options off the cuff. What this is doing is actually going back and deleting every file that's sitting in the root of the repo called big_video.mp4. Now, that would work in terms of drastically reducing the size of our repository, but it's not the best thing to do because it means that you're actually going to lose all of those versions of that file. And you're probably versioning that file for a reason. So instead, you can run this git filter branch command. Now what this does is it goes back and runs the LFS track command against every single commit in your repo, converting them all into pointers, and then removes all of those large blobs, which is pretty cool. It was actually built by Andy Neff, one of the core Git LFS contributors. However, there is a much, much simpler way that doesn't require mind-bending auditing of command line flags, and that is the BFG repo cleaner. Has anyone used the BFG before? The repo cleaner, not the gun from Doom? OK, cool. Well, this was built by Roberto Tiley, who's a developer at The Guardian in the UK. Basically, it was built initially to kill history from Git repos. So I think he had a problem where someone had committed something sensitive to a repository quite a long time ago, and then he had to go back and remove every instance of that and didn't want to deal with filter branch, partly because it's complicated and partly because it's very, very slow. One of the problems with filter branch is, again, because Git is a mishmash of shell and C, is it doesn't have a persistent process. So filter branch tends to walk your entire DAG when it goes back and makes changes, which can be very, very expensive. Now, the BFG repo cleaner is actually built in Scala on top of JGit, which is a complete reimplementation of native Git in Java. And it does have a persistent process. So it actually memoizes all of the different trees and blobs that it's processed and then doesn't touch them again. So there's a big spreadsheet on the BFG repo cleaner's homepage, which has the filter branch commands and the equivalent BFG commands running side by side on a bunch of different projects. And it varies between 10 and 720 times faster, depending on the depth and shape of those repos. And the reason I'm talking about it today is because as of version 1.12.5, the BFG repo cleaner has built-in support for Git LFS. So instead of this, you can you can install the BFG using your package manager of choice. Again, it's Java, so it runs on every platform that Git does, basically, or every platform that has a JVM. And you can run the BFG convert to Git LFS command instead and pass it a set of patterns which you want to start tracking using LFS. Now, there is one slightly arcane flag you have to pass as part of that called no blob protection. Basically, what that is just indicating to the BFG to rewrite the commit you currently have checked out as well. So by default, the BFG doesn't rewrite your currently checked out commit under the assumption that you've already changed that to be correct. But you just need to remove that protection using no blob instead. So if you know which large files you want to start tracking using LFS, then you can just run BFG and you'll be fine. However, if you're working on a very large repository or a repository that's changed in structure a lot over time, for example, Jira is, 12, 13, 14 years old now. So it has a lot of history and there's been a lot of refactoring. So if I wanted to go back and identify where potential large files are, I'd have to actually walk back through the history because we've been moving directories around and potentially renaming files as well. Now, fortunately, a gentleman named Charles Bailey from Bloomberg recently open sourced a set of scripts called Repo Factor on GitHub. Now, what these scripts do is they let you actually identify large objects throughout the history of your repository. And they're even more clever than that. They actually figure out when you've moved objects around and then do calculations based not just on the current size of the object in your history, but also if that file has changed a lot. Because if that file has changed a lot, then that means that you've got multiple versions of that blob that are being potentially poorly delta encoded, and there'd be a much bigger impact if you remove those ones from your repo's history. So to use Repo Factor, as I mentioned, I didn't call it an application because really it is a set of command line tools or scripts that let you introspect your repository history. The first thing you want to do is run this thing called generate larger than. And it gives you some kind of curious output. What this is a SHA-1 hash of a blob, so the identifier of it sitting inside your DAG, followed by the size on disk of that blob, followed by the average size of that blob as it's been changed over time. So for every time a file is moved, it'll actually calculate how similar it is to another blob, and then put those into a chain, and then give you the average size of that chain. So the higher that average size, the better a candidate it is for Git LFS tracking. So once you've got a collection of these blobs, you can pipe it to the add file info command, which basically runs it through the Linux files command, which inspects it for, I'm not exactly sure how it does content sniffing, but it'll give you a little bit more metadata about what that object is. So now we can see we've got a couple of PNG images of reasonably high resolutions. And then if we pipe that to sort, we can start sorting by that third field. So that means that the better candidates for LFS tracking will float towards the top of the list. Then we can write that out to a text file, and then run the report on large objects command, again from that same Repo Factor repository against it. And then at this point, it will actually give us the paths to those files. So now we can tell exactly which files we should be tracking with LFS. And this is a really valuable tool, particularly if you've got a deep history in your repo. So once we've got those, we can use that as input for our convert to Git LFS command, and then we should have a nicely compressed history of our repository. So once you've got your history rewritten, then you need to figure out where you're going to host that. If you're using Bitbucket Server, you can enable large file storage on any repository once you've upgraded to Bitbucket Server 4.3 or above. Enabling it's really easy. You hit a checkbox in the repository settings. And it's got some nice stuff, like it'll read through to your Git LFS store when it's rendering diffs or source displays inside the UI. Or if you're using pull requests, you'll see the properly inflated image or binary or whatever instead of just those pointer files. So that's how you migrate to Git LFS. Now I want to talk a little bit about some tips for using LFS in a team context, because so far I've really only been talking about how individual developers interact with their repos. Now the first thing you need to know about working with binary data in a repository is you need to be really, really careful about merge conflicts. Now no one enjoys merge conflicts, but at least with a text file, you can kind of see each other's changes and then merge them together using whatever diff tool you're using. Unfortunately, with binary merge conflicts, there usually is no way to merge those things. Typically, it means that one person is going to have to reapply their changes on top of whatever the other person has done. And there is nothing more depressing than spending all day working on some new change to a video or a model object or a texture file or whatever you're working on, and then finding out that someone else has also been adding some stuff to it, and you're going to have to go back and reapply those changes again. Now, fortunately, version control systems have sort of solved this problem in the past already through locking. Now, Git being a distributed version control system, locking is sort of the antithesis of what you want, because the whole idea is that each developer has their own copy of a repository. They can make whatever changes they like to it, and then you resolve those changes later on into one central, blessed repository that the team uses. Now, locking solves the problem that you get with binary files, but feels a little bit weird in a distributed context. Now, unfortunately, it hasn't been implemented in Git LFS just yet, but there is some work on the master branch in the Git LFS repo up on GitHub, which is leading towards it. So there's a couple of commands that have been implemented, and Steve Streeting, actually Atlassian's major contributor to the Git LFS project, put together a proposal on how locking should work in Git LFS in the future. And as part of this proposal, it's kind of cool. I can put up a link for it later. But he goes into quite a lot of detail about how locking should work in a distributed world. And he first starts off the proposal by saying how locking definitely should not work in Git. It's kind of interesting because if you sort of went to naively implemented locking in any version control system, you'd probably think logically, well, okay, if a developer is going to make some changes to a file, maybe they're going to create a branch, then they're going to acquire a lock on a file, and that's going to prevent other people from changing that, and then eventually they're going to release that lock and merge their branch back into master. And that sounds logical, but there's a couple of problems with that. Let's imagine, under that system, if a developer is working on the master branch, and they want to change their large gray image of an elephant, they might acquire a lock on that, make some changes, and then release that lock. Now this looks okay, but imagine if I was a developer working on another one of those branches, and I also wanted to make a change. Because under Git, you're used to being able to do whatever you want on any particular branch. And this sort of breaks that model, because all of a sudden, you're restricted from doing work on those branches. So how do we allow developers to use branches and yet ensure that we don't have binary merge conflicts? Well, Steve's proposed a multi-branch locking model that solves this problem. And the big idea around how multi-branch locking works is that you sort of forget about branches. And you say, OK, any developer can acquire a lock on a file, provided that it is the most recent version of that file in existence, irrespective of which branch it's on. So how this works in practice is just say that same developer acquires the lock on master, makes some changes, and then releases the lock. If a developer working on a feature branch also wants to make some changes, if they try and acquire a lock, sorry, the color's a little bit washed out here. That elephant in the middle is pink on the far left. If they try to acquire a lock on their version of that file, then that lock is going to be rejected because they can't modify it because there is a newer version of that file in existence. So what they have to do is bring that version of that file onto their branch. So for example, they could merge master into feature 1, or, as is a little bit more clean, they could rebase their branch on top of master. And then they will have the latest version of that file, and Git LFS will allow them to acquire a lock and make their changes. So this works okay, but there are some situations where maybe you don't want to rebase on top of that branch or merge that branch in because there's some changes on there that potentially conflict with what you've got, or maybe you're working on a stable, a fix on a stable release branch and you don't want to bring all of those changes from master in. Well, if that's the case, so say on feature 0, what you can do is actually just cherry pick that individual commit over onto your branch, which brings across the latest version of that blob. Or you can even just grab that file and copy it over manually, or do a git checkout of that particular file over your working copy. As long as the SHA-256 hash of that object is the latest version that Git LFS knows about, then it'll allow you to acquire that lock and make those changes. So this is really neat, because it's a kind of a, locking is kind of an ugly concept when it comes to distributed version control. But they've built this system where you have kind of this separate orthogonal thread of file locking that runs across and orthogonally to your feature branches. So it means that you can avoid merge conflicts, binary merge conflicts, but still have a fairly elegant workflow on top of it. Now, the lock commands that are currently being implemented are really easy to use. There's git lock, which locks a file, git unlock, which unlocks a file. One cool thing to note about unlock is that you can actually unlock other people's locks as well. So the locking is sort of meant as more of a guidance than like a hard and fast, this is how you absolutely must work. Again, just sort of keeping within that distributed version control system model. They're sort of considering at the moment whether they'll require a force or not as part of that. And then you can list a list of locks that have been applied to your particular repository using the locks command. Now, as I mentioned, this isn't fully implemented, or in a released version of Git LFS yet. So in the meantime, until locking is implemented and released, I advise just making sure if you are making changes to a large file that anyone else who's likely to make those changes knows that that's the case. So manually pass the mutex over whatever chat solution you're using. So now I want to talk a little bit about how you can pull the content from other members of your team, as well as just push and pull your own. So if you've cloned a repository that contains Git LFS pointers before you have LFS installed, then basically you just have a checkout with all of those LFS pointers sitting around on disk. There's a special command you can run called Git LFS fetch, which will actually go and retrieve the content and replace those pointers locally. And you can also pass the -- recent flag to that in order to retrieve content that other users have contributed to branches that you have checked out locally. And it considers anything that's been modified in the last 7 days as recent. So basically, that's any branch that has a commit on it that's newer than 7 days old. And if you like this behavior, you can set that to permanently be true by setting the fetch recent always flag. This is particularly useful if you're planning on going offline for a little bit and you need to review some other team members' changes. So for example, if you're about to jump on a plane, sort of makes Git LFS a little bit more distributed again by giving you more repository content to work with. There's also some other properties you can set to tweak this behavior. So you can change that sliding window of 7 days by setting fetch recent refs days. You can also make it retrieve content for commits that aren't branch tips by setting fetch recent commits days. So that means that if you're planning on doing some cherry picking or some rebasing while you're offline, you can use that to retrieve content from other commits on those branches. Now, just a word of warning, that can be incredibly noisy if people tend to make lots and lots of changes per day on the same branch. And you can even set fetch recent remote refs to true. And what this does is instead of just grabbing LFS content for local tracking branches, it retrieves any content for every branch that the remote knows about. And sorry, not just branches, but tags as well. So that could potentially be a very expensive operation, both in terms of disk space and the amount of time it takes to download. So unless you work in a very small team or in a very slow-moving project, I don't really recommend turning that on. Now, once you've been working with Git LFS for a while, you're going to end up with that little .git/lfs/objects directory growing and growing and growing in size. Now, disk is fairly cheap these days, but probably eventually you're going to want to clean that up. And to do that, you can run a command called git LFS prune. Now, what this does is it goes off and deletes any large objects that are sitting in that cache that Git LFS thinks you don't need anymore. Specifically, it runs through like a very careful list of rules, because obviously you want to be careful when you're cleaning up data. It won't delete anything that is currently checked out. Makes sense. It also doesn't delete anything that is referenced by a commit that you haven't yet pushed. So it does that by looking at your remote refs and your local refs and looking at the differences in commits there, and anything that's referenced by something in that delta, it won't delete when you run prune. And it also, if you've got the recent commits or recent commits or recent ref settings that we just looked at enabled, it also won't delete anything that is considered recent. And you can also configure it by using the prune offset days command. So that changes the recency test up or down, depending on what you want to do. And you can also turn on the prune verify remote always flag if you like. And this one I actually do recommend, and I'm sort of surprised it's not a default, because what this does is it actually checks using the LFS API whether the object it's about to delete exists on the server. So if you're using LFS in production in a proper development workflow, I do recommend turning this on because it means that you're basically guaranteed to never accidentally lose data that hasn't already been previously stored. So that's how you can retrieve more data from the server. Now I want to talk a little bit about some situations where you might want to delete, where you might want to retrieve less data and actually leave some of those pointer files sitting around on disk instead of pulling down the large content that's associated with those. I'm going to go back to the video games analogy again. Imagine you're following a proper development workflow and you're writing lots of unit tests and functional tests, and then you have this CI job set up that's just going to run the tests against your code base. Now, if it's unit tests and it's just building the code, it potentially doesn't need all of those huge graphic assets and models and whatnot to do that. So in order to save huge amounts of bandwidth, you could pass the exclude flag and use the value asset / to leave those things as pointer files instead of pulling down that large content and save a huge amount of time. Or you may be a specialist on your team and only require a certain subset of those large files. So you can use the include flag and say, hey, I just want to pull down the audio files, for example. And then that will pull down, and then that'll, again, leave everything else as pointers and just inflate that one directory. Now, you can make these permanent using fetch exclude and fetch include. And the pattern there is just a simple ant glob, which you're probably already using in your git ignore files inside your Git repositories. It's exactly the same spec. These days, IDE and Git GUI support is pretty good for LFS. The JetBrains family of IDEs, I haven't actually seen an official statement from JetBrains yet, but they do appear to work, whether you're using Android Studio or AppCode or IntelliJ. The Git LFS support seems to be working OK. If you're using Eclipse, it absolutely works with LFS as well. However, you do need to upgrade to eGit Team Provider version 4.2. So Eclipse's Git integration is based on eGit, which is based on JGit. So it's actually a complete re-implementation of Git in Java. So you need to upgrade to 4.2+ to have support for those pre-push hooks that Git LFS uses. However, Git LFS hasn't been ported over to Java yet, so you'll also need to make sure you have Git LFS on your path when you start your IDE. NetBeans is a slightly different story. They shell out to Git for all of their operations. So it just works out of the box, provided, again, that you have LFS and Git on your path. There's a bit of bad news, though. Xcode doesn't support LFS, primarily because Xcode runs on top of a forked version of Git that Apple maintains. And the version that that's forked from doesn't have support for some of those extension points, notably that pre-push hook. So if you are using Xcode for development, you might have to use a Git GUI client, for example, SourceTree. Full disclosure, I work for Atlassian, and we maintain SourceTree as a free Git GUI that you can use to interact with your Git repos. And in fact, the original developer of SourceTree, Steve Streeting, is the same guy who contributes to Git LFS and initially built that GitLab project. So SourceTree has top-notch support for LFS. I think the bundled version of Git comes with Git LFS as well, so you can just download SourceTree and use it. And it also searches for error cases. So if you don't have that pre-push hook installed in a repo, it'll pop that in there for you. And it knows to look for pointer files and things that haven't been inflated if you have those LFS repos sitting around on disk already. So that's all I've got today. If you want to learn a little bit more about the project, the documentation is really good up on github.com. You can check out the source code and potentially think about contributing to. It's interesting not just from a large file storage format, it's a point of view. It's actually a really interesting project that extends Git. So if you're interested in building your own extensions on top of Git, taking a look at how Git LFS works is a good starting point. As I mentioned, its bundled support is in Bitbucket Server version 4.3 and above, and we've publicly committed to bringing it to Bitbucket Cloud as well in the very near future. And if you have any questions, I think I've got a little bit of time left. Otherwise, definitely hit me up on Twitter if you want to talk more about Git or Bitbucket or Jira or any of the Atlassian product suite. Thank you very much.